So
I don't remember, is the final exam cumulative?
it is,
Okay.
yeah, but it's not going to be everything because it's impossible to write an exam that covers everything we did.
I think
So-
it'd be really awesome if you left out a little pause question.
We'll see.
I would agree with that.
I'm gonna curate the list. I'll put out a study guide after the second midterm. Fine. Yeah. Well, pause is the one thing we really have to cover though, because you need that for vibrations 431.
I'll learn it again.
Lucky you.
I understood it well a couple weeks ago.
Yeah. He has to deal with like housing stuff, instructional and media. You're in ticket. No, I'm sorry. At least we're all more. I signed up for him. I don't use the two. Then they're about the same, you know,
Can you check the answer of the
It's just that you marry.
receipt part?
Okay.
Of the problem field?
Okay.
Because I got it.
Okay, yeah, send me an email and then I'll check I'll check.
Okay, and this, right, and my work.
Exactly, yeah.
Okay. Can I send you by this?
Yeah, that's fine.
I don't think we have the gas. Yeah, chef, she knew. Yeah, I think she's also teaching around. Did we have time to post it? I know, yeah. Kind of possible. Yeah. She's like, so you're gonna pay for this? And I was like, oh my god, we're gonna schedule a meeting, 30-hour telling them we're gonna go. And they say, no, I know. Okay, that's fine. I won't worry about it, you know. And we just have to do this to all of us. You go, eat, like with their mom. Or maybe someone else, you know, I'm. If your mom's okay, maybe. Come with us, teach you. You know, down you go. She's like, okay. She'll let you go. Huh? Yeah, if you can go down. I don't know if she knows she wants to, she's gonna. You know what you Yeah, it's really why, okay, I like it, yeah, but I feel like. Yeah, it's because I realized a lot of like, not Hispanic, they don't like shoot too much. No, I don't recognize them. Yeah. The last time I ate two birds, yeah. Yeah, because I was making fun of, I guess all the friends that I know. You know, like drinking styles and sure. I don't know, that's such a good. I should have eaten healthy. And then to my mom, yeah, I'll take your mom once a day. And your dad could be eating our breakfast. I guess you can go for yeah, what did they say about me? That they like to, I money, Not me, keep it. That's enough. Actually, no, I don't think there. I can't believe that they made it. I don't know, just talk.
All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Been good, hopefully. It's been cold lately. It might rain a bit later, but hopefully everyone's staying dry, staying warm. Okay, so today we're gonna continue with our lecture that we started on Tuesday. So Tuesday we kind of introduced this idea of a random variable, talking about a little bit of probability, reviewing a little bit of statistics. Today we're just gonna dive a bit more into that. Today we're gonna get a little bit more into mathematical statistics. I think probably most of the things that we went over on Tuesday, you guys have probably seen in some capacity before. But maybe some of the stuff we're covering today might be new, but it's a lot of the same stuff that we went over last time. It's just a little bit of a different perspective, a little bit more of a mathematical kind of interpretation of okay. All right, and so biggest thing is we have our midterm exam next Tuesday in class here, so make sure you guys are here in class for that. It's very similar in format to the practice midterm that I posted earlier this week. It's just I made it a little bit shorter than that practice midterm though. All right, question from the chat. Okay, covering. Yeah, so on the exam, there's going to be a little bit less of a focus of Fourier transforms, just because we kind of covered those a little bit late. So there's definitely going to be more focus on the vector calculus stuff and the Fourier series expansion. So I would definitely focus your studying on that, but Fourier transforms will still be there, but probably more as a conceptual question, more than a problem that you're actually going to work out. Yeah. And yeah, I would have to double check with the textbook. So if it's on the study guide, the study guide should be pretty consistent with the textbook. But yeah, I don't have the textbook in front of me, so I don't know what exactly those sections refer to. But I would just double check with the study guide and use that as your reference for studying. Yeah. Cool. All right. Any questions about anything before we get started for today? Oh, and since someone asked before class today, so we are getting pretty late in the semester. Pretty much right after the second midterm. We'll start preparing for the final exam. So final exam in this class is cumulative, but it's not going to cover absolutely everything in the class, just because it's impossible to have just one exam cover 15 weeks of content. So it is going to be a curated list, probably maybe anywhere between 60%, 65% of the class. You'll be expected to know for the final. I am going to put out a study guide for the final exam. So, if you haven't been looking at the study guides for the midterms, definitely look at the one for the final, because I don't want you studying the entirety of the class for the final exam, because that's just way too much. So, yeah, so you can look forward to that probably after the second midterm. Maybe the week after we take the second midterm exam. Okay. And I know we haven't had any review sessions for the midterm, just because there's just so much content we have to cover in this class. But for the final exam, I have reserved the final lecture for this semester as a review session for the final exam. So we will get a chance to review before the final. Okay. All right. So let's go ahead and start the lecture for today. And so topic for today is going to be random variables. Okay. And in particular, we're going to be talking about how to represent a random variable mathematically. And so we're going to be going over probability distribution functions, or probability density functions. Okay. All right. So first, let's kind of review a little bit of the terminology that we went over on Tuesday. Right. So on Tuesday, we made this distinction between two different types of variables that we typically work with in engineering analysis. Right. We have a deterministic variable. Okay. So a deterministic variable has just a singular value. So it doesn't matter how many times you observe this variable, how many times you evaluate it, it's always going to have just one value. Okay. So an example of a deterministic variable, let's say we have a variable named x, right? So if the value of x is 5 and it's a deterministic variable, then x is always going to be 5, because it has just one predetermined value. Okay. Now, most of the time, when you're taking a math class, or when you're taking an engineering class, most of the time we work with deterministic variables, just because they're a lot easier to work with and use in calculations, right? And so if you know exactly what the length of an object is, if you know exactly what its density is, what its weight is, the acceleration due to gravity, right? These are all examples of variables that we often take as deterministic. So we can use them in equations and calculations. It's just a lot easier that way. Okay. But the focus for this last section of the course is going to be on random variables. Okay. So a random variable has a different value every time you observe it or every time you evaluate it. So the primary example that we use for a random variable is to quantify your commute time, right? So every time you commute to campus, every time you drive here, you walk here, you bike here, it's always going to be a little bit different because, you know, traffic conditions are going to be different every time, you know, stoplights are going to be different every time, right? It's never exactly the same, right? So for a random variable, you know, I think probably the simplest way to evaluate to show this is to represent it using a range, right? So maybe our x here is going to be 5.7 to 6.4, right? So what we say is that, you know, every time we evaluate x, it's somewhere within this range. Okay. So it can be as low as 5.7, as high as 6.4. You know, there's some variation. Okay. All right. In reality, you know, most variables are random, right? And so you always have to deal with some degree of uncertainty, you know, when you are dealing with real life measurements or real life observations. Just because naturally there's only so many things that we can control for, you know, as an engineer in a particular system, right? Just for example, right? So if you're working in aerospace engineering, you're designing rockets for launch, right? You don't really have that much control over the weather on the day of the launch, right? Whether it's a hot or dry day, or whether it's a cool and humid day, if there's any rain or excessive fog, right? These are things that you can't really control over. And so those are always going to be random variables that you have to account for in your design. Okay. And so knowledge of random variables and how to deal with them, I think, you know, personally, I think is something that's really undertaught in kind of traditional engineering curriculum. So, you know, that's why I wanted to spend a little bit of time in this class talking about it. How do we represent these random variables and how do we even work with them to begin? Okay. Okay, so what we're going to do today is, you know, how can we, you know, how can we better represent these random variables, you know, a bit more quantitatively than before, right? Okay, so what we kind of reviewed on Tuesday was kind of more traditional metrics or traditional descriptions of random variables. So some examples of this would be, you know, the mean of a random variable, the median of a data set, mode, right? Right, so these are all terms that, you know, you guys have probably seen before in other classes or other settings, okay? We even did a little bit more advanced stuff like variance, standard deviation. Okay. Right, so I would call these kind of the traditional metrics or traditional description of random variables, just because they're kind of the easiest to kind of pick up and kind of really understand. So even if you express a random variable as a mean, you know, there's still some understanding, or there's still kind of a an implication that this random variable can change, but the mean is kind of the average value of that random variable. Okay. Okay. But there are more descriptive ways to describe a random variable that tell us a lot more information about it than these just kind of traditional metrics. And that's kind of what we're going to go over. Okay. Because you know what, just like we talked about last time, you know, the mean can be really misleading for a random variable or a data set. The median can be very misleading. The variance can be very misleading. So, you know, if you have better descriptors or better ways to describe your random variables, you'll have a much better grasp of how you know, what the uncertainty is like, and you know, how much variance there is in your data set. Okay. Okay. So that was just kind of a review from last time. Any questions on this so far? Okay. All right. So let's talk about cumulative distribution functions or distribution functions. All right, so oftentimes you'll see cumulative distribution functions shortened as CDF. And so you'll see me use that you'll see me use that acronym quite a bit. So CDF just stands for cumulative distribution function. Okay. Okay. So let's start with the definition. So kind of the terminology that you know that you kind of have to get used to is that every random variable can be described by its own CDF. Okay. So we say that the CDF of a random variable okay. And just for simplicity, we'll give this random variable a name. So we'll call it X. And so what the CDF represents is the probability that that a particular observation or a particular evaluation of X is going to be less than a particular threshold. Which is, a lot of words, but it's a lot simpler to understand than that is. Okay. But let me give you the exact definition first, and then we'll talk about some examples to kind of illustrate this. Okay. All right. So the cumulative distribution function on CDF is usually given by a capital letter. Right. So we'll call it capital F, and usually we have a subscript, and that subscript there describes which random variable it's assigned to. Okay, so every random variable is assigned a CDF, or we can use a CDF to describe it. Okay. And so what we say is that the CDF, capital F of our random variable X, right? This is going to be a function of T. Okay. This represents P, where P here represents probability. That the value of X is less than or equal to T. Okay, so let me label this. All right, so this expression here this represents the probability that the observed value of X is less than or equal to a certain value T. Okay. Okay. So one thing with just mathematical statistics in general is that the terminology and the expressions can be very intimidating. But I think once you kind of see some examples, it's really clear. Okay. So let's do an example really quick to kind of illustrate what a cumulative distribution function looks like. Okay. So let's take a random event, one that hopefully everyone's familiar with if you've ever played board games before. Let's talk about rolling a dice. And just to be clear, I mean rolling a very standard dice, six-sided dice. I'm not sure if anyone here plays Dungeons and Dragons, but dice can come in very, very many shapes and sizes. So yeah, just standard Monopoly dice, six sides. Okay. Okay, so what do we know about rolling a dice? Granted, you're not playing with your uncle who cheats at gambling and the family party. Generally speaking, there's about a roughly equal % chance of rolling any particular number on dice. Right? Okay. In fact, we can compute that, right? And so if we know that there's 6 sides of the dice, and every time you roll, you're going to get one, one side of that dice is going to come up, right? The probability of rolling any particular side of that dice is 1/6. Right? Or if you want a percentage of this, we can just compute 1/6. That is about 16.67%. Okay. Right, so the chance to roll a 3 is 16.67. The chance to roll a 4 is 16.67%. Okay. All right, so let's plot out, or let's show, what the cumulative distribution function for rolling a dice would look like. So let's plot, not pot. Okay. So the value of a dice is a great example of a random variable, because every time you roll the dice, you're going to get a different number, right? But at the same time, the amount of allowable values for rolling a dice is constrained. It's either going to be 1, 2, 3, 4, 5, or 6. Okay. So let's see what that would look like, right? So if we plot the cumulative distribution function, okay, so the cumulative distribution function is going to look something like this. All right, and then let's mark on the horizontal axis all of our possible values for rolling a dice. So let's do 1, 2, 3, 4, 5, 6. Okay. Okay. So let's go back to our definition for the cumulative distribution function. So the cumulative distribution function represents the probability that when we observe the value of this random variable, it's going to be less than that particular threshold. Okay. So the entries on our horizontal axis here, that represents our threshold, right? So these are all our possible dice values. And what do we compute up here, right? The probability of getting any particular face of value is 16.67%, right? So right at the beginning here, right at 1, right? Our cumulative distribution function is going to start at 16.67%. Right? Okay. Now we get to the value of 2, right? So when our cumulative distribution function has a value of 2, that's going to represent our probability that our dice roll is going to be 2 or less. And so that's both 2 and 1. And so the probability of rolling a 2 or a 1 is going to be double that probability, right? And so we're going to go up by another 16.67%. And so what is double that? That's like what, 33, that's 1/3, right? So 33.34%, right? Okay. Then we get to 3, right? And so with when the cumulative distribution function reaches 3, right? That represents the probability that our dice roll is going to be 3 or less, right? So that means 3, 2, or 1. So that means we're going to go up by another 16.67%. And so this gets us at about a 50% probability, right? So probability of rolling 3, 2, or 1 is 50%, because that's half the number of faces on a dice. So hopefully you guys are seeing the trend, right? So every time we go up in value for the cumulative distribution function, we're going to add 16.67%. Okay. And so we're going to go up some more at dice value of 4. So then this is, I'm not going to go all the way to the vertical axis, but this right here is 66.67%, 2/3. Going to take us all the way to 5. And so at 5, I should have given myself some more room. At 5 here, that's what, 83.34%. Right? And then all the way when we get to 6, right? And so at the value of 6, then our cumulative distribution function is going to reach 100%, because the probability that you're going to roll a dice and you're going to get a 6 or less is 100, because the dice only goes up to 6, right? So this right here is 100%. Okay. Okay. So that's what a cumulative distribution function looks like. So, we did a fairly simple case with the dice, but you can use a cumulative distribution function to represent any random variable. Okay. All right. Any questions on this example here? Okay. An interesting one if you want to get into gambling. So growing up in a Vietnamese household, I learned a lot of this growing up, but this was more playing cards and blackjack. So you learn to kind of calculate these in your head when you're playing blackjack with your uncles who don't necessarily play fair. Yeah. Okay. All right. So let's talk about cumulative distribution functions a bit more. Let's talk about some of their properties. Okay? Okay. So first property that you hopefully see from this example is that CDFs are always increasing, right? So they are what we call monotonically increasing. Just based on the way that CDFs are defined, it's impossible for a CDF to ever decrease in value, right? Because remember, the value of the CDF at any given value that represents the probability that our random variable is less than that. Okay. And so because of that definition, CDFs are always going to be increasing. So as you read a CDF from left to right, it should always be increasing in value. Okay. Okay, number two property for CDFs is that they always cap out at a value of 1, which represents 100%. Now, in the previous example, I used percentages just because typically with probabilities we talk in percentages, but in reality, CDF are traditionally represented using decimals and 1.0 being kind of the top. Okay. Okay. Another property for CDFs that is pretty useful is that you can use CDFs to compute the probability of whether a random variable fits within a certain threshold or a certain range. Okay. Okay, so for instance, let's say that we want to compute the probability that the value of x lies between two thresholds, A and B, right? So the probability that A is less than or equal to x, which is less than or equal to B. Okay. So we're setting both an upper bound and a lower bound for our x. We can compute this by taking the difference fx of b minus fx of a. Okay. So we're basically using the cumulative distribution function and we're subtracting it at 2 different points, within that distribution function. Okay. And because of the property of CDF being monotonically increasing, and we know that b is greater than a, then this quantity here should always be positive. Okay. So let's do one more example of this and and talk about kind of a bit more of a typical case with our commute time. Okay, so you can use a distribution cumulative distribution function to talk about a random variable like that. Before that, any questions on the properties of CDFs? Okay. All right, so let's look at a CDF of typical commute times. Okay. All right, so remember, CDF represents the probability that your commute time or the random variable here is going to be less than a particular threshold. Okay. Now, it's actually not that common to have a CDF that's kind of beautifully described like this. Usually, you evaluate the CDF at certain points, at certain fixed points, right? Okay. So this is going to be an example of CDFs defined at certain key points. Okay. So let's have T, capital T here. This is going to represent our commute time. So this is the random variable we're using to represent our commute time. Okay, so let's evaluate its cumulative distribution function, or let's say what the value of the cumulative distribution function is for certain thresholds. Okay, so let's say that we want to evaluate our CDF at 10 minutes. Okay. All right, so this represents the probability that when you commute to campus or when you commute to work, it's going to be less than 10 minutes. Okay, so let's say that you can get the commute under 10 minutes only on a really good day. So let's say that there's very little traffic. You're in kind of a trailblazing mood. So the traffic laws kind of become traffic suggestions. You run that red light or something. So the probability that you get your commute time under 10 minutes, we'll say, is about 15%. So we'll say 0.15. Okay. Okay. Let's increase the threshold a little bit. So let's compute, or let's theorize what your commute time would be at 12 minutes, right? So the probability that your commute time is less than 12 minutes, this is probably a bit more likely, right? And so let's say this is maybe 0.35. Okay, so 35%. So still has to be a pretty good day. But maybe less things have to go right. You can break a little bit less traffic loss to get your commute time under 12 minutes. Okay, so let's look at the CDF. So let's increase our threshold to 14 minutes. This is a pretty comfortable time. Most days you're going to get in under 14 minutes. So this is, let's say this is 0.7. All right, and then we'll do kind of the final one. So the final one here, we'll say it's 20 minutes, right? Right, pretty much, every day, let's say every day you get in before 20 minutes. And so the CDF at 20 minutes is 1 point. Okay. Okay, so a definition like this is a little bit more common. And so of course you can plot this now. And so if you wanted to, you could make a plot of the CDF just based on these data points. But this is a little bit of a more common way to define a CDF. Okay. Okay, and of course, you can take a data set and produce a CDF from it. And so you can see just what percentage of the data points is less than 10 minutes. That's your CDF value for the first one, and 12 minutes and 14 minutes and so on and so forth. Okay. Okay, good. All right, and so with the CDF, we have a little bit of a more thorough definition of a random variable than simply just its mean and variance, right? Okay. Because with the CDF, you can compute the mean from a CDF. That's not too hard. We'll talk about that, very soon. But rather than just a single value or single values of mean and variance, you have this entire function or lots of data points to describe your random variable. Right? So if we kind of revisit kind of the first kind of comparison that we went over today, okay. And so if we kind of make the comparison between a deterministic variable versus a random variable. Right? Where our deterministic variable here has just a singular value. So we say x is equal to 5, right? Always going to have that one value. There's no uncertainty in that at all. Now we have another way to describe our random variable. So our random variable, instead of giving a value for it or a range, we can instead describe it using its CDF. Okay. And that's much more of a descriptive way to describe the possible values of that variable. Okay, good. So CDFs, CDFs is kind of the first introduction to mathematical statistics and representing these random variables in different ways. Okay. Although I would say it's not the most common way to represent a random variable. So the most common way that you'll see when you read kind of mathematical statistical papers on probability, you'll most likely see probability density functions. Which, funnily enough, the theory of density functions was created kind of before modern computing. And so the acronym for probability density functions is PDF, but most people associate PDF with something different nowadays. Okay. All right. So what is a probability density function? Right? So a probability density function is a function just like a CDF, but it represents the value of your random variable or the possible values of your random variable in a slightly different way. Okay. So to kind of introduce this, so let's go back to our the idea of a histogram that we introduced on Tuesday. All right, so the histogram was a graphical representation of a random variable, okay, or a data set, which shows the relative frequencies of certain values that the random variable takes each time that you evaluate. Okay. All right, and the way that we view the histogram was kind of as a series of bars, where the height of the bar kind of shows you that the random variable is more likely to take that value more than the others. Okay, so let me kind of draw one just to kind of show you. Okay, so histogram, usually looks something like this, right? So we have kind of bars that look like this. Right? Let's say they're increasing. Okay, and after a certain point, they start to decrease. All right, so the height of the bars. Okay, so the height of the bar shows the likelihood that our random variable will take those particular values. So the highest bar shows the highest likelihood. So on the horizontal axis here, we have possible values for the random variable. And on the vertical axis here, we have essentially probabilities. Okay. All right. So histograms are great. Actually, there's a wealth of information that can be gleaned from a histogram because they tell you a lot more information about the random variable, more than just its mean and its variance. Okay, because you can actually see you can actually see the values of the random variable broken down into different bins, right? And you can see which values are more likely than others, right? So what I drew here, this is a fairly boring histogram, so it has just kind of one pronounced peak. But it is actually possible to have multiple peaks in a probability distribution function or a histogram as well. Okay. So I kind of spoiled it a little bit. And kind of the reason we're bringing up I'm bringing up histograms here is that a probability distribution function essentially represents the same information as a histogram. In fact, you wouldn't be incorrect to say that, they are essentially the same thing. So a probability density function and histogram, they represent the same thing. The only thing that's different about a probability density function is that it actually has a functional form. So there's a mathematical form for the probability density function as opposed to just the graphical form. So for a histogram, the only way that you can, view a histogram or interpret a histogram is to look at the graphical representation. For a probability density function, we actually have a mathematical function representation for. All right, so PDFs, will have a mathematical formulation, and this has kind of an important consequence that it usually makes our PDFs a relatively smooth function. Okay. And so if we took that same random variable that had the that had the histogram above, we can graph its probability density function as well. Okay, so if we graph that same function here, or once again on the horizontal axis, we have possible values. And essentially on the vertical axis here, we have probability. So for a probability density function, for a unimodal function like that, it probably looks something like this. So this represents the same information as above, just instead of several different boxes or several different levels here, we just have one kind of smooth function. But just like before, the height of the function at any given point represents the relative probability that our random variable can take that value. Okay. And so from this information here, usually what you're going to look at with the probability density functions are the locations of the peaks. Okay. So whenever you have a peak, that's going to be a very likely value. In this case, since we only have one peak, one maxima, we have just one expected value or most likely value for our random variable. Okay. So probability density functions are used a lot, and they're used to kind of represent data a lot. Have you guys heard of the term like a bell curve before? Yeah, so that's kind of where this kind of comes from here. So bell curve represents a very common density function called a Gaussian or a normal distribution. So we'll be going over that one specifically. That's a very common way to represent random variable. It's also used for grade distribution that some professors use, but that's probably the context in which you probably have heard it before. But the world of density functions is actually very vast, and so there's lots of different types of density functions that you can do. So there's uniform distributions, there's beta distributions, there's gamma distributions, Gaussian distributions. It's really cool, and there's a lot to really unpack here. All right. Any questions so far on probability density functions, PDFs? Okay. All right. So let's talk about some properties of PDFs before we jump into some examples. Okay. So first property of a PDF that we will go over is its relationship to the CDF. Okay. So the probability density function and the cumulative distribution function for a given random variable are actually related to each other, and they're related based on their derivative. Okay. So the derivative of the CDF will give you the PDF. All right, so if we take the derivative. So remember, we represent CDFs with a capital letter usually, so capital F subscript X, okay? This is gonna be equal to little f subscript X as a function of T, okay? So this little f here, this is the PDF of a random variable X. And this big F here, this is the CDF of our same random variable X. Okay. And then by that same token, you can do the reverse as well. So if you have a PDF of a function, if you take its integral, the integral of the PDF will give you the CDF of that same random variable. Okay. And so if you take the integral from minus infinity to infinity of the PDF of a function with respect to t, okay, that will give you the CDF. Okay. Okay. So that's probably the most important property, is that it is related to the CDF. Okay. I think CDF is a little bit, it's the reason usually CDFs are introduced first in a class like this, just because they're easier to interpret. It's easier to come up with examples with a CDF. But just know that it is very closely related to the PDF. Okay. Other properties of the PDF. So PDFs, obviously they can decrease, and so that's not going to be the same as a CDF. But PDFs are always going to be positive, or what we say they're non-negative. It doesn't make sense for there to be a negative probability for a certain event to occur, or a certain value for our random variable. Okay. So it's important for our PDF to be non-negative. Another important property is that it has to be continuous. Okay. There cannot be any discontinuities in a probability density function, at least not in the traditional sense. For certain situations, you could have a discontinuous PDF, but those are for cases where you have a finite amount of outcomes, or a finite amount of events that can occur. So actually rolling a dice is a good example that would have a discontinuous PDF, because our CDF was also discontinuous. All right, then number 5. Number 5 property here is that the integral, the total integral for a PDF will always give you 1. In fact, I just noticed that there's a typo in property 2, and I'll fix that in a second. Okay. So actually, if you take the integral of the PDF for the entire range of possible values, so from negative infinity to infinity, you're always going to get 1 in that case. So the integral from minus infinity to infinity of your PDF, this has to equal 1. Okay. And so the typo that I had above is with respect to the relationship between the PDF and the CDF, right? And so, we have this exact same integral twice. And so if we integrate from minus infinity to infinity, that's going to give you 1. And so if you want to relate the PDF to the CDF, right? So actually, let me circle the typo here. So this is the main typo here. So if you want to relate the PDF to the CDF, you can't integrate all the way to infinity. Instead, you're going to integrate up to a certain finite value. So you should only integrate up to a value t. So I apologize for that. So that was a typo that I did a couple minutes ago. Okay. One last property before we jump into an example. Okay. Just like we had for CDFs, oftentimes we're interested in the probability that our random variable falls within a certain range. Okay. We can do the exact same thing with our PDF, except instead of evaluating the PDF, we're going to be taking the integral instead. All right, and so we call this interval probability. So basically the probability that our random variable x lies between two thresholds A and B. Okay. So the probability that A is less than or equal to x, which is less than or equal to B. Okay. The way that we can solve for this using the PDF is we take the integral from A to B of our PDF as a function of t. So this is the same interval probability property that we had for the CDF, except instead of evaluating the CDF at two locations, we're instead taking the integral from A to B of that PDF. Okay. So those are the main properties of PDFs. Any questions on this so far? Okay. All right. So the reason PDFs are so I would say so widely used is that there are a lot of really well-known PDFs that describe certain different behaviors for random variables. Maybe not all random variables will fit into these PDFs, but they are so widely used that people often use them to describe random variables, and people will kind of know what they would be. Okay. So the first common type of PDF that is often used is called the uniform distribution. So a uniform distribution represents a random variable that has basically a completely random, evaluation, has no preferred value, but it does stay within a certain upper bound and a certain lower bound. Okay. So this represents random variables that can take any value within a certain range. And every value within that range has equal weighting or equal probability. All right, so the PDF for a uniform distribution looks quite simple. Okay. So to define a uniform distribution, you need a lower bound and you need an upper bound. Okay. So we'll call that A and B. Right, and the uniform distribution between A and B is just a flat line, right? So it looks literally like this. Okay. All right, and so that means the value of the random variable X can take any value between A and B, and there's equal probability of that value landing anywhere within that threshold. All right, and so if you want to represent kind of a true, I would say random variable, uniform distributions are often used for that. Okay. That means the random variable can take, a value here, and they're equally as likely to take any of these values here. Okay. So what we say is that there's no preferred value within this range, but the random variable is constrained to stay within that range. Uniform distributions are nice because mathematically they're very easy to deal with. They're just a constant value. And so the main example that we're going to do, probably most likely next Thursday, is going to be for the uniform distribution. Okay. Number two. So the number two most common PDF that's used to describe a random variable is a Gaussian distribution, or some people like to call it a normal distribution. Or another name, probably more commonly it's known as, is the bell curve. Because it looks like a bell. Okay. All right, so for a Gaussian distribution, the most telling feature of a Gaussian is that it has a very clear preferred value. So there is a clearly defined maximum, a clearly defined peak in that Gaussian distribution. Okay. Okay. So the PDF for a Gaussian distribution is going to come up, right? And so it's going to come up, it's going to max out at the most likely value, and then it's going to come back down again. Okay. Okay. Now, what's interesting about the Gaussian distribution is that, once you have the peak defined, you're equally likely to land either to the left of the peak or the right of the peak. Okay. And so what we say is that the Gaussian distribution is symmetric around its peak value. All right, so the reason the Gaussian distribution is very popular is that it has a very strong connection to, I would say, kind of the more traditional ways to describe randomness. So concepts like the mean, concepts like the variance and the standard deviation, they connect very naturally with the Gaussian distribution. Okay. So let me kind of show you what the Gaussian distribution looks like. All right, so once again, I'm going to draw a graph here. Okay, so for a Gaussian distribution, there's a very clearly defined peak. Okay, and so let's say that our probability distribution function is going to look like this. All right, so that's a very typical Gaussian distribution. So there's a very clearly defined preferred value. Okay. All right, so if we trace this peak down, we look at its location on the horizontal axis, right? This is the most likely value for the random variable. All right. So that's the location of the peak, right? Now the width of the curve is actually very interesting. So the width of the curve tells you how varied the value is, right? So you'll have some Gaussian distributions that are much wider and some Gaussian distributions that are much skinnier. Okay. So the width of this peak. Okay. And so what we can say is that the width of the Gaussian peak tells you the range of possible values that your random variable can take. Right. So Gaussian distributions with a wider peak, with a much wider one, will have a larger range of possible values. But there is still a preferred value. There is still a most likely value that's given by the peak. Okay. Okay. Now these concepts, right? So this concept of having a very clearly defined value, this concept of representing a range of values, that connects very naturally to how we think of random variables most of the time, right? So the most likely value, right? This is essentially the same thing as the mean. Right, so if you took a Gaussian random variable, you sampled it or you evaluated it 100 times and you compute its average value, the mean, it's going to be right at the peak or very close to the peak. Okay. And the width of the peak here, okay, this is the same thing or the same concept as the variance. So the wider your peak, the more higher amount of variance that you're going to have in your random variable. Okay. So that's why Gaussian distributions are very, very popular, just because, they connect, very strongly with our understanding of mean, our understanding of variance and standard deviation. Okay. Okay. Any questions on the Gaussian distribution so far? All right. In fact, the definition of standard deviation actually came about based on the definition of the bell curve or the Gaussian distribution. Okay. Okay. So a term that you'll hear a lot, especially, when you're talking about, rankings of certain things, right? You'll talk about how many standard deviations you are away from the mean. Right? Right, you might have heard this term, when you're talking about, like SAT scores or things like that, right? So there's the mean SAT score, and you want to be, certain amount of standard deviations above the mean, or or maybe your standard deviations below the mean, right? Okay, so what does that mean, or what does that mean for kind of relative, relative ranking, right? Okay. So let's go over kind of the most common terms, and this is kind of more trivia. So I would say that, not a lot of statisticians talk like this. This is just mostly for people who take, these kinds of things and try to make something of it. But I would at least want to tell you this just so that you know. So if you're one standard deviation within the mean, okay, basically your score or your ranking or whatever, if you're within one standard deviation away from the mean, that means you're within the middle 68% of the distribution of the possible data. Okay, so remember, if we say that mu here represents the mean and sigma represents the standard deviation, right? And so the probability that u, or the random variable x, right, is greater than or equal to mu minus sigma, which is less than or equal to mu plus sigma. Okay. So the probability that you're within that range right there, right? So one standard deviation less, one standard deviation more. Okay. The probability of this occurring is 68%. Right, and so if you go up to two standard deviations, so two standard deviations, you are, if you're within two standard deviations, you are 95%, 95.5% likely to be within two standard deviations of the mean. So the probability of mu less than 2 sigma is less than or equal to x, it's less than or equal to mu plus 2 sigma, is 95.5%. Okay. Okay, so for example, so if you look at kind of the average height of humans in America, right? So there's a mean height, but let's say, and we know the standard deviation as well. And so, let's say that the mean height of people in America is 5'8". Let's just say, okay, taller than me. And let's say the standard deviation for that is 3 inches, right? And so if you add two standard deviations to that, so you go 5'8", you add one standard deviation, you're at 5'11", you add 3 more inches to that, you're at 6'2". Okay. So if you are 6'2" or higher, then you are taller than 95.5% of other Americans. I don't know if that's the exact numbers. I think the average height is around 5'8", 5'9". But I'm not sure what the standard deviation is. That's probably something you can look up. So that's usually the context under which it's used. Okay. All right. Any questions on this? Okay. One last kind of really interesting fact about the Gaussian distribution that is its primary weakness, honestly, is the fact that the Gaussian distribution is actually unbounded. So what that means is that, most of the time, when you look at a data set that is Gaussianly distributed, you're gonna be, most of the data points are gonna be around the mean. But Gaussian distributions don't rule out the possibilities of having outliers, okay? Okay. So if you're sampling a Gaussian random variable, so you're just pulling value, it's possible to get some values that are completely out of left field, okay? And let me kind of show you why that's the case. So if you look at how the Gaussian distribution is plotted here, I know it's not the neatest plot, but you can see here that once you kind of get far away from the peak, the PDF of the Gaussian distribution actually does not go down to 0. Okay. Same thing over here too, right? So that means technically it's possible within a Gaussian distribution to get a value that's way, way far away, okay? Now the probability is really, really small, but if you have a very, very large data set, likely you're going to have 1 or 2 or 3 data points that are really far away from that don't follow the trends at all, okay? And that's a weakness because sometimes, sometimes you don't want to make it possible to have such outliers, okay? And so the terminology that we typically use for this is that these are values that exist in the tails of the distribution. So you'll hear that term a lot. So you'll hear this. You'll say that you'll hear terms that this distribution has a significantly long tail, or we have values that exist in the tails of the distribution. That's just kind of another word for outliers. Okay. I think they use that term because if you look at a dog or a cat sitting down, their tail kind of forms that kind of flat shape. All right. Any questions on this before we wrap it up for today? Okay, all right. So next time I see you guys will be on Tuesday for midterm 2. So remember, homework 6 is due this Sunday. I will post the solution for homework 6 on Sunday night, just so that you can have it to help you study for the exam as well. Okay. All right. So thank you guys for coming today. I hope you guys have a good weekend. If you have questions before the exam, don't be afraid to email me. I will answer those, and I will see you guys next week. My solution for homework 4 don't only have the, okay, I'll double check that. Yeah, so I do have the full solution for homework 4. Yeah, I think I might have just posted the wrong file. So yeah, thanks for catching me. Hi, Professor. Hey, Evan, how's it going?
Good, and yourself?
Good. What's
Tau
up?
beta pi?
Oh yeah,
Trying
You
to get
joined?
it. Yeah.
awesome.
Well, I had a question. I know you have a background in finite element analysis.
Yeah.
I was wondering if you have any research opportunities open during the summer that relate, or even if they don't, it's fine. Like,
So the way I do research is that I usually have students kind of come up with their own projects.
okay,
So I don't have any external funding right now.
okay,
So if you want, we can talk. Maybe we'll talk maybe sometime at the beginning of summer.
okay.
And we'll see if we can come up with the project for you. I do have some small things that I could have done.
Okay,
So let's talk at the beginning of summer.
that'd be great. Thank you,
Yeah.
Professor.
Mhm.
I have a quick question for you.
What's up?
So electives that I wanted to take, they're taken already.
Yeah.
So I seen that we were talking about me taking the laboratory for spring.
Yeah.
But I could still take it in the fall, right?
Oh yeah. We can do that.
Yeah,
As
because
long as you take the lecture first, then you can take the
like I can take them concurrently.
Oh yeah, you can take it at the same time.
Oh, okay.
Okay, Johnny, what electives were you trying to get in?
FEA
Did
and
FEA fill up already?